braving the rain, storm, unexpected humidity, and making the trek up to IUCAA. Thank you very much. I see a lot of regular.
Always good to see new faces. Welcome. Today we are really happy to welcome Professor Matthew Colless, who's from the Australian National University. Actually, he's come here as part of a bunch of people who have come from the university to talk to us at various places in India about various collaborations, academic collaborations between India and Australia, in particular with the Australian National University. Matthew is the director of the Research School of Astronomy and Astrophysics at the Australian National University. He and I go back long back. I first met Matthew maybe 35 years ago. That gives away my age. His as well, I suppose. At the University of Cambridge, where he was a few years ahead of me in the PhD program there, and since then we've worked together on various occasions. He was for 9 years the director of the Anglo-Australian Observatory, and has gone back to becoming the director of the astronomy, this research school at the ANU. And in between, of course, as I said, he did his PhD in Cambridge, a bachelor's from Sydney, and after that he had other positions, postdoctoral positions at Durham, Cambridge, at Kitt Peak in Arizona, and has been involved in some of the most important observational cosmology projects that have taken place in the last couple of decades, I would say, including the largest redshift surveys of galaxies that have been done. And he'll tell you, he's interested in mapping out the large-scale structure of the universe through galaxies, and to find how galaxies are moving through these large-scale structures. He used to be a vice president of the International Astronomical Union, and of course, he's as Australia is a partner in one of the largest telescopes that are coming up, the Giant Magellan Telescope. He is part of the board of the GMT as well. So we welcome Matthew to Pune. It's his second time in Pune, first time in IUCAA, and I hope he's going to tell us about how to find or not find aliens.
Thank you very much, Shomak. Look, it's a great pleasure to be here in Pune again. It's a long time since the last time I was here. Last time I was here, I was using the Giant Meter Wave Radio Telescope with a student of mine. It's very nice to be back again, even though this is only a flying visit. I noticed that Shomak referred to some of you as regular faces here, and I assume that means the rest of you are irregular faces. I have to put my hand up to that too. I also have what could be considered an irregular face. However, it's not an alien face, and in fact my talk tonight is about how a lot of things out there in the universe are in fact not aliens. So weird and wonderful astronomical phenomena, but with natural explanations. Let's see, is this thing going to work? Ah, yes, there we go. Excellent. So this is not really a talk about aliens. All of those of you who thought this was a talk about aliens, I suggest now is a good time to leave, because there will be absolutely no aliens in this talk. The first time I gave this talk, about half the audience stood up and left at this point. So I added this, the clue is in the title, it's not aliens. This is really a talk about some weird astronomical observations that some people suggested at some point might have been aliens or some alien artifact, but which in fact are most likely to be unusual, in some cases highly unusual, astronomical phenomena, but these are entirely natural phenomena. The talk really comes out of my desire to convince people that aliens is almost never the right answer for the weird and wonderful phenomena that we find all the time in astronomy. And the basic scientific principle behind this is that you don't explain weird things by invoking unknown entities until all the explanations involving known entities are exhausted. And of course, this has been summed up best by Carl Sagan, who said that extraordinary claims require extraordinary evidence. And aliens, you would have to admit, constitutes an extraordinary claim. Now, this is not to say that aliens don't exist. Maybe they do, but they shouldn't be the first choice of explanation for whatever weird phenomena you happen to have stumbled across, or even the second choice, or the third choice, or the fourth choice. As I'll show you, some extraordinary things out there in the universe can be perfectly well explained, often by more than one explanation that doesn't involve aliens. And all of this was triggered by the remarkable case of Boyajian's star. How many of you out there know about Boyajian's star, or Tabby's star, or the WTF star? Hands up. Okay, so a few of you at least know what I'm talking about. So this is a remarkable star, which has at least a couple of times been claimed might be evidence for the existence of alien megastructures, whatever those might be. So here are the questions I will attempt to answer in this part of the talk. First, did astronomers really find evidence for an alien megastructure around Boyajian's star? Secondly, what the hell is an alien megastructure anyway? What did they find if it's not an alien megastructure? And what non-alien explanations might there be for the weird observations? So, just in case you're on the edge of your seat with excitement, the answers are very unlikely. Maybe this, I'll show you in a moment. What did they find? Well, some pretty weird stuff. And what are the non-alien explanations? Well, that's a really good question. And in fact, what I will come up with is a surfeit of potential natural explanations, but not the right explanation. We don't know the answer just yet. So let's set the scene here. Boyajian's star, which is also known as Tabby's star, or the WTF star, or this telephone number, is an odd, unique, and very, very strange star. There's no question but that something weird is happening there. But the question is it really aliens? Tabby's star, or Boyajian's star, is one of about 100,000 stars that are being studied with the Kepler satellite. Kepler's looking for planets orbiting other stars. It's looking for transits, planets that pass in front of the face of a star, causing a very small dip, usually less than 1% dip, in the light that we're seeing from that star. Here's the Kepler satellite, and it's staring at a star here. The star appears to be about 100 meters away. In fact, the stars are a little further away than that. In fact, they're halfway across the galaxy. Here's a more realistic picture. This shows you the location of the sun in the outer spiral arm of the galaxy, and about 1,000 light years away, here is the search area. I mean, Kepler's looking over this whole depth, but the main cluster of things that it's looking at is typically of order a few thousand light years away. And it's looking in the constellation of Cygnus. Here's Cygnus the Swan, and this is the Kepler field that it's staring at and was staring at for several years. So Kepler's actually discovered thousands of planets. That's its main mission, and it's been incredibly successful, and that's a wonderful talk in its own right. But I'm not going to talk about any of that. What I'm going to talk about is this one weird star. And that telephone number that it's known by is, in fact, its Kepler catalogue number. Tabby's star is somewhat more massive, slightly hotter, and brighter than the sun. In other respects, it's a fairly ordinary star in many ways. It's about 1,300 light years away, and it's much too faint to be seen with the naked eye. Here's a bunch of information about Tabby's star that you can find if you go and look up on Wikipedia. And as you can see, as it says over here, this is in solar units. It's 1.4 solar units. It's 1.6 solar radii. It's about 5 times the luminosity of the sun, and so on. But in many ways, it's actually not a particularly interesting or different star. What is weird about it is what it shows up in its light curve. What Kepler's doing is staring at the star and just measuring its brightness. Now, for most stars, that gives you a whole bunch of nothing, right? All you see is the light curve goes along and it does absolutely nothing for thousands and thousands and thousands of days. And that's what Kepler saw for most of those 100,000 stars. But for a few thousand of them, it saw these tiny dips in the light curve, and those tiny dips turned out to be periodic, and that's the signature of a planet that happens to be passing in front of the star along the line of sight from the star to Kepler staring at it. And that was Kepler's main mission and what it did very successfully. But amongst all those stars, there was one star which was very odd indeed. Now, in fact, this is the paper where they first started talking about this star. And the reason it's called Boyajian star or Tabby star is that the lead author on this paper is T.S. Boyajian. And the T stands for Tabitha, and Tabitha is shortened to Tabby. So Boyajian star or Tabby star is based on this paper. The WTF is not what you thought it was, not at all, no. It actually stands for Where's the Flux? Okay, and if you thought anything else, you're completely wrong. No astronomer would possibly make such a pun in a paper title. The other thing that you could do is read the abstract of this paper, and you will find absolutely no mention of alien megastructures anywhere in this paper, right? There's no hint in this paper whatsoever. Tabby Boyajian is completely not to blame for claims about alien megastructures. I'll come back to that in a moment. The question is, what did they claim? Well, what they did was they took 4 years of data of Kepler staring at the star, and most of the time, of course, what you see is a whole bunch of nothing. But in fact, on this star, what they saw were these enormous great, jumped ahead of myself there, these enormous great dips here, and here, and here, and here, and a whole bunch of grass, little dips all the way along here. Now, as I said, when you're looking for a planet, when a planet passes in front of a star, even a planet as big as Jupiter, you typically get something on the order of a 1% dip in the brightness of the star. Now, when you look at these dips, these are 15%, 20% dips. These are humongous dips. You've got to block 20% of the light of a star in order to produce a dip as big as that. And you've got to do it fast, too. That's the other thing you can see, is these dips don't last very long. They go down and they shoot straight back up again. If you look at them in detail, in fact, you can see that they're very brief indeed. 0.4 of a day wide, that dip, right? That's a, 8% dip, something like that. So something's got to go across the face of the star in less than half a day and still block 10% of the light of a star. Now already, you should be doing some geometry in your head and thinking, well, that's actually rather hard to do, right? It's got to be in very close and it's got to be very big in order to block a star which is 1.5 times the radius of the sun. So, 1.5 million kilometers across. That ain't easy to do. So these are pretty bizarre data, right? The dips in the light aren't periodic. They're random, so they're not something that's simply orbiting and doing the same thing again and again. They can be very deep. As I said, one of 15%, one of 22%. It clearly isn't a planet. The dips in the light are way too big. As I said, Jupiter would only block about 1% of this star's light, and those dips, of course, would be periodic. The planet would be going around in a nice regular orbit, and the dips would recur at some interval. None of that is true. It isn't another star because we'd actually see the other star. If it was one star going in front of another star, we'd see the other star. Our data's good enough for that, so it's definitely not that. Whatever is blocking the star is big. It has to be up to half the width of the star itself, right? So we're talking 750,000 kilometers across. And you can see where the thought of megastructures is starting to bubble up in some people's brains at this point. There are lots of these dips in the star's light, hundreds of them. They don't seem to be periodic at all. Every periodogram, every analysis that's been done doesn't seem to show anything periodic. And they've got odd shapes too. It's not a nice disk going in front of the star with an easy on, easy off shape to its light curve. They've got funny jaggedy bits. They're asymmetric. They're sharply on and softly off. They're softly on and sharply off. They're not anything easy to predict. But there's also, on top of that, there's also a modulation, an apparent change in brightness that seems to go up and down every 20 days or so for weeks, and then completely disappears, and then comes back again. So it's not periodic, but it's not aperiodic either. So people have made lots of suggestions for what this could be. So let's rule out quickly some of these things. One of the things it's not a problem with the telescope. The researchers have gone to a lot of trouble to check out the Kepler data, and in fact, as I'll mention later, people have looked at this star with other telescopes now and see the same things that Kepler sees. It ain't a problem with a telescope. They're real. It's not due to star spots. This is another thing people thought. Maybe this star has got giant versions of sunspots on it, half the size of the star, dimming the light as they whiz around. Well, They've got to whiz around pretty quick, right? Remember, these are coming and going in half a day, and this is an F-class star. It's a big star. So this type of star doesn't have enormous spots. It doesn't rotate fast enough to do it. It's not going to be star spots. It's not due to planets smashing together and creating lots of dust to block the star's light. If it was that, then first of all, you'd have to find lots of planets to do all the smashing together, given all the time that's involved here. But the dust would be warm. It'd be illuminated by the star's light, and you'd get an infrared signature. And there's no sign of this infrared light from warm dust. In fact, as I'll show you later, the lack of an infrared signature from warmed dust is one of the hardest things to explain. So there's some things that might be left in these scenarios. One of them is a clumpy interstellar medium. In other words, dust, nothing to do with the star itself, but in the interstellar medium somewhere along the line of sight between us and this other star, which is absorbing the light. It wouldn't get warm, of course, because it's too far away from the star. It's in interstellar space. It's cold. But it's just this one star. There's 100,000 stars. Why is there just one star which has got interstellar dust passing in front of it right now? Another one is intervening objects. Some weird ring system or something. Yeah, maybe. I'll show you a couple of examples of people who think it could be something like that. Another one is circumstellar material. Planets in the act of formation, or swarms of asteroids or comets around this star. Again, there's pros and cons to that, but it's not completely crazy, and I'll talk a bit more about explanations that do that. And then last but not least, we've got our old friend the Dyson sphere, aka alien megastructure. I need a sort of alien megastructure voice, but I'm not very good at doing that, so I won't inflict that on you. So what's an alien megastructure? So this whole thing came about because a guy called Jason Wright, an astronomer, a genuine real astronomer at Penn State University, suggested that the dips might be due to some giant structure like a Dyson ring or sphere. So a Dyson ring is a ring that goes round a whole star. A Dyson sphere is a sphere that actually encapsulates a star and captures all its light. Or perhaps just a vast swarm of solar panels was surrounding Boyajian's star. So again, to give Jason Wright his fair due, what he said was, aliens should always be the very last hypothesis you consider, but this looked like something you would expect an alien civilization to build. Okay, so I don't know what Jason Wright thinks an alien civilization would build, but I don't really know what I would expect an alien civilization to build. I also don't know that it was the very last hypothesis he uncovered, but he covered himself a little bit by saying this in his paper. So this is the idea. You've got a star and you're wrapping around it some enormous, great, big structure, a ring, a series of rings, or an actual sphere. These are the idea of an alien megastructure. So here's a really cool picture, absolutely based on nothing whatsoever but the artist's imagination. No connection to any science whatsoever here, but it's really, really cool, and I thought I'd show it to you. So, apart from the very bold assumption about aliens built into this suggestion, it also has some other much more physical problems. The megastructure has to be big, right? To block 20% of the star's light would take solar panels that would cover an area of over 750 billion square kilometers. So that's solar panels covering about 1,500 times the area of the entire Earth. There's also the old puzzle about the infrared. No matter what aliens do, they can't get away from the second law of thermodynamics. Some of that light, no matter how efficient their solar panels are, is going to be absorbed and re-emitted as heat. And in that case, you would expect to see that 20% of the star's light. Even if only 1/20th of that leaked out, you should see a 1% infrared signature, and the limits on the infrared signature are tighter than that. The lack of periodicity also means that the structure must be changing, either its composition or its orbit, and doing it fast. Remember, these things come and go in a day or even a fraction of a day, and disassembling and reassembling a Dyson sphere is not something you do in half a day, no matter what you think nanobots might be capable of doing. The alternative explanation, and my personal favorite, is that it's just traffic jam. So having driven across Pune twice today, this one has a certain appeal to it. But again, I don't think that's really what's going on. So what other explanations out there might actually work? What natural explanations might work to explain Boyajian's star? So what about a swarm of comets orbiting the star, each of which would be surrounded by gas and other material that could produce the dips seen? So the comets themselves are small, but their tails, their gas and dust tails, are enormous, and maybe they could produce the dips seen. So people have suggested, you've got these comet fragment families. So you've got whole families of comets orbiting this star, and with the gas and dust from them, you get the pearls on the string type arrangement that we've seen for comets that are fragmented in our own solar system. These might orbit past the star and cause this sort of a dip. Well, this explanation at least has the value that we've seen comets orbiting other stars previously. We know such things exist. Comets aren't something that are unique to our own solar system. We've seen them around other stars from as long ago as the 1980s. In the exoplanetary disk surrounding the star Beta Pictoris, we see infalling, evaporating bodies, which is another way of saying comet in fancy language. And there are well-documented cases of this, well-modeled, where we know that what we're seeing is something very like a comet falling into the sun, doing the same thing around Beta Pictoris. So maybe that could work, but still, the lack of any infrared signature is still very puzzling. It's not too damning in this case. If another star happened to pass nearby, its gravity could disturb the first star's Oort cloud of comets, the region billions of kilometers out where we think most, if not all, of a star's comets actually reside. And this disturbance could send those icy chunks flying down towards the other star, where they could break up, creating all these weird dips. The ices in them would heat up, blow off as gas, and that could explain the odd shapes of the dips. But it's still hard to see how these irregular swarms of comets could produce, for very short periods, 15 to 20% dips in the star's light. Right? The comets have got to come and go across the face of the star in a day or so. Not crazy, but not easy either. There's another problem with Boyajian star, which is what we call secular dimming, which just means the star itself has been changing its total luminosity quite substantially. If you believe the historical record stretching back over 100 years, then over a 100-year period, which is, of course, as nothing in the life of a star, there's been a 20% drop in the total luminosity of Boyajian star. And if you just limit ourselves to the period covered by Kepler, where we've got spectacularly accurate photometry, then in fact you see that it's been 3% over the 4 years. Now a 3% change in the total luminosity of a star is not easy to do. There are ways you can do it. Such things do happen. There are pulsations, there are star spots, there are all sorts of things. But combined with the much shorter dips that we're seeing in the light, this is an interesting change. And there's nothing we know about in, for example, the cometary swarm hypothesis that would make this plausible, right? Why is there suddenly an increase in the total amount of comets, and how are they blocking out the overall light of the star for long periods? All right, so another possibility. What about a planet which has rings, not just one ring, but a whole series of rings, so a super Saturn with lots of rings around itself, and Trojan asteroids. So, we've got a weird star, so we're having to create a very weird solar system to explain it. So the idea is that some of these dips are due to the planet passing in front of the star and its rings occluding the star, and then other dips are due to these Trojan asteroids. So these are asteroids that are trapped in the Lagrange points, the saddle points of the gravitational potential in the star-planet field, and so they're trapped there and they produce some of these other things. So the idea here is they're trying to offer a relatively natural solution, only using phenomena previously observed, though perhaps in larger or more massive versions, they say with massive understatement. We model the system using a large ring body whose transit produces the first dimming, and then the swarm of Trojan objects sharing its orbit causes the second period of multiple dimmings. Our model allows us to make two straightforward predictions. This is good, a model which makes predictions we can actually go and check. We expect the passage of a new swarm of Trojans in front of the star starting in early 2021, and then a new transit of the main object during the first half of 2023. So this is a nice, clean prediction. Got to wait a few years to actually check it out, but it's a reasonable model with a prediction that we can clearly check. It'll either be right or it will be wrong. It won't be hard to test. Here's the idea. You've got this planet with an extensive ring system passing in front of the stars. Either side of that ring system, you've got the Trojan asteroids stuck at the Lagrange points of the orbit. These are 60 degrees away in the orbit from it. And you can work out a suitable orbit where the timing of the ring system and the Trojans is just right to explain the observations of Kepler between 2009 and 2013. And then, of course, all this thing passes around the star. You get a secondary eclipse in 2017, not seen, sadly. And then in 2021, you begin to see the repeat of the pattern that we've already seen before. So, a nice straightforward thing, a strange setup, but not crazy, and with good prediction. So, a model we can check. Another model that's been tried, and this is actually quite interesting because the people on this paper are a bunch of amateur astronomers. I use the word amateur here advisedly, actually, because these guys are obviously pretty damn professional. This is actually quite an interesting paper. Published in Monthly Notices of the Royal Astronomical Society, they suggest that these dips might be caused by a brown dwarf with an associated ring system on a 1600-day elliptical orbit, transiting icy moons of the brown dwarf, sublimating near closest approach to the star, like comets, then could provide an explanation for significant dips seen by Kepler. So this isn't completely different to the other one. Instead of a planet with rings, now it's a brown dwarf with rings. And instead of being Trojan asteroids, these are swarms of icy comets producing the dips. So here's the basic idea. These are the rings of something transiting in front of Boyajian star. And by looking at the dips, you can reconstruct a ring pattern that actually gives you the dips you see around Boyajian star. You get the orbital parameters. And in fact, here's a mapping of their ring model to what Boyajian star actually produced. And it's not bad. Now, of course, this is not prediction. This is post-diction. They created the rings in order to map this structure. But again, they're predicting that this will repeat on a 1600-day orbit. So again, nice predictive situation. So many models have been done. Observations have been taken. I haven't shown you all of it. This isn't just to talk about Boyajian star. What I've been doing is showing you one case where something was really hard to understand. It's really very difficult to understand, and showing you that there are a number of natural models which could explain it. In fact, there's an interesting paper that came out in January this year by our old friend Jason Wright, the alien megastructure man himself, called A Reassessment of Families of Solutions to the Puzzle of Boyajian Star. You should read this paper. It's all of about 1.5 pages long. And I will summarize it here. He goes through all the different families of possible solutions for this puzzle and tries to say whether they're still worth considering or not. So he says instrumental effects are not worth considering. It's been checked. It's fine. It's not the data. The second one, he says, is explanations involving only opaque objects such as stars, planets, swarms of asteroids, or alien megastructures are now ruled out. There's no way that you can reconcile the colors, the lack of infrared, various other things with opaque structures. It's not an alien megastructure, says Mr. Alien Megastructure. Models involving interstellar dust are supported by the DIPS colors. Now that they've got multicolor data, they can make it work, but you've then got to grapple with the fact that there's no increase in gas column density. This is dust without associated gas, which is hard to come by in general. It's not fatal, but it requires some special pleading or a neat model. Intrinsic variability of the star, once thought to be ruled out completely, now has got a little bit more theoretical support and might be consistent with the multiband photometry, though why this would be so rare and only seen in this one particular star is actually a very difficult problem to solve. Stars are actually very simple. They're usually very common. If it's in this one star, it should be in lots of other stars, and we don't know why it wouldn't be. The measured reddening of the dust, the actual change in the spectral shape that you see as these dips occur, may favor circumstellar material. It's actually not too inconsistent with that, and that moves that family of models, all the various ones we've talked about, up in plausibility. but they still struggle with the lack of the near-infrared excess, the same old problem about things having to be warmed up. The fact that the colors that you require for this imply very small dust grains, which typically have a short lifetime as well. And again, the lack of gas accompanying this fine dust is still hard to explain and would seem to argue against a cometry type solution, where in comets you typically are sublimating ices and you get gases as well as dust. Another explanation which has come up is an intervening black hole. So in this case, you've got dust or some sort of failed circumstellar disk around a black hole, and that gets you away from the infrared excess problem because the black hole is essentially cold. Nothing is falling into it, no light is heating the dust, so there doesn't have to be gas sublimating, and there doesn't have to be any infrared excess. So that's an interesting suggestion that's come up. But who knows? What I've shown you, I think, is that there are multiple ways in which natural phenomena could explain even this very, very weird 1 in 100,000 star. The only way we'll know is by doing more observations and getting more data. So, back to the telescopes. All right, let's leave Boyajian's star behind and look at some of the other weird things that have been claimed to be aliens. This is an interesting paper describing 3 weird types of transient radio phenomena. One of the weird types is actually very weird, but a well-known type, which is pulsars, radio pulsars. These are a strange and interesting object in their own right, very heavily studied across the way here at NCRA, but although they're weird, undoubtedly, they're very definitely natural and well-known phenomena. The second weird phenomenon was what's called a Lorimer Burst, which was the prototype of an exciting new type of radio source called fast radio bursts. These were very unusual back in the time 2012 when this was actually published. This is work done in Australia with the Parkes radio telescope. And in fact, fast radio bursts are now being detected more and more often and are again known to be a natural phenomenon. But at the time, they were very weird and not known. The third class of things were called peritons, which this paper said were probably a form of peculiar radio frequency interference. So what they actually said in another paper in 2014 was in trying to identify terrestrial sources of these peritons, they've looked at airborne aircraft, radio frequency emissions from electronics and lightning phenomena, all sorts of things. They also wanted to look at narrow bipolar pulses and terrestrial gamma flashes. I don't even know what those are. But they listed a large set of radio frequency emissions and failed to identify them. Chirped radio bursts, said Katz in 2014, known as peritons, are consistent with plasma propagation, but an astronomical origin has been excluded. Dodin and Fish, on the other hand, said these enigmatic down-chirp signals that are detected by radio telescopes may be produced by ball lightning. We explore a scenario in which peritons, that sparker and fast radio bursts, are all atmospheric phenomena occurring at different heights. So let's be fair, here that no one's calling them aliens, but they are invoking a vast range of different things. And then along came Emily Petrov and ruined everybody's day. Subsequent tests revealed that a periton can be generated at 1.4 gigahertz when a microwave oven door is opened prematurely and the telescope is at an appropriate relative angle. Radio emission escaping from microwave ovens during the magnetron shutdown phases neatly explains all of the observed signals of the peritons. In fact, they could have realized this by just noting the fact that all the peritons had been observed either at lunchtime or dinner time. So this rates not as a detection of alien life, but as detection of an unintelligent, non-alien life form, namely radio astronomers using microwaves while their telescope is operating. Here's something, however, that has been sometimes claimed to be a potential alien signal. This is what's known as the WOW signal. And the WOW signal was a strong radio signal observed just once in 1977 by the Big Ear radio telescope during a SETI program. So these guys were actually out there searching for extraterrestrial intelligence, and in the middle of that they saw an enormous great Burst. It was a signal at a frequency in a narrow band near the hydrogen line at 1420, the infamous waterhole where they were searching for extraterrestrial signals. It appeared continuous for the 72-second observing window of Big Ear. Big Ear's sweeping across the sky, so it only observes one position on the sky for 72 seconds at a time. And this appeared to be continuous during that 72-second window. But of course, every time people have gone back to look, many, many times, no similar signal has ever been seen. So, is this aliens? Well, yes, it could be, but it's very weak evidence. It's 72 seconds of a continuous pulse signal seen one time, once, ever, only. So other explanations are possible, but in fact, there's no really good explanation for what this was. It's just too little data to constrain the models to tell us what this might be. So the jury's out on this. But extraordinary claims require extraordinary evidence. This does not constitute extraordinary evidence. So what might be extraordinary evidence? How about aliens on Earth, right? If aliens were on Earth, that would surely be great evidence, right? So there are endless claims of aliens visiting the Earth, and the evidence for most of those claims is so flimsy it's not worth even wasting the breath to dismiss them. But what if we actually found an alien corpse on Earth? What if we found something that looked like this on Earth? So this is actually a CAT scan of some strange skeletal remains that were discovered in the Atacama Desert, the very dry Atacama Desert of Chile in 2003. In the Atacama, bodies actually mummify in the open air, and this was a tiny mummy that was found. And it's extraordinarily strange. I mean, look at the features on that. Surely this is evidence of aliens? Well, no. Sadly, the corpse, which in fact, as you can see from that top picture, is only about 15 centimeters long, is actually human. And there's been a detailed DNA analysis of the remains, which was published not so long ago in Genome Research. And it clearly shows that it's human. It belongs to a premature baby girl, nicknamed Atta, after the Atacama Desert, who likely died at birth from a whole series of malformations due to several gene mutations, which are known to be linked to bone formation, musculoskeletal development, thyroid function, collagen production, all of which could have produced these strange deformations of her skull, of her body, and the fact that her bone structure looks like that of a well-developed but very tiny 8-year-old. So, no, sadly, no evidence. So Samuel Johnson once said that patriotism is the last refuge of the scoundrel. So I'm going to appropriate the quote and say that aliens are the last refuge of the unimaginative. Almost all the evidence that's claimed to be aliens is simply lack of imagination. The universe is extraordinarily strange. So, while Boyajian's star is probably not an alien megastructure, suppose you actually wanted to go out and actually find an alien megastructure. How would you go about that? Well, in fact, this amounts to searching for what are known as Kardashev Type 2 or Type 3 civilizations. Kardashev Type 1 civilizations are those that actually are able to harness the entire energy resources of their planet. So humans, this is a log scale, are, if you're generous, about a Kardashev 0.5 civilization. That's pretty generous. Kardashev Type 2 civilizations harness the entire energy output of a star. We are nowhere near that. That requires stellar scale megastructures, the sort of thing that was being talked about for Boyajian's star. Type 3 Kardashev civilizations control the entire energy output of their home galaxy. And this requires hundreds of billions of megastructures to grab all the light from all the stars. How would you go about doing that? Well, that infrared signature we talked about as being one of the things that damned an alien megastructure around Boyajian's star is in fact a great way to search for extraterrestrial civilizations of Kardashev Type 2 or Type 3. And in fact, our old friend Jason T. Wright has been out there doing just this. He has been searching for extraterrestrial civilizations with large energy supplies using wide-field infrared surveys to detect the waste heat, right? No matter how good your civilization is, no matter how great your tech is, that old laws of thermodynamics still get you, and you're going to produce waste heat. If you're collecting all the light of a star, a tiny fraction of that light must be leaking out of your megastructure, no matter how efficient, as infrared light. And they show for the first time that Kardashev type 3 civilizations, i.e. ones that are actually absorbing most of the light from a whole galaxy, are, and this will be a big surprise to all of you, I'm sure, very rare in the local universe. They actually went away and looked for Kardashev type 3 civilizations, for looking for things that were as big as a galaxy, glowed in the near infrared, and more particularly what they were doing for the astronomers in the audience, they were looking for a predicted offset of these galaxies from the optical Tully-Fisher relationship, right, which basically tells you the luminosity output of a galaxy in terms of its size and or mass. And what they actually found was an upper limit that at most 0.3 of all galaxies are inhabited by Kardashev type 3 civilizations. So only one galaxy in 300 at most is hosts a Kardashev type 3 civilization. So this sort of structure in the universe is surpassingly rare, very rare indeed. Extraordinary claims require extraordinary evidence, said Carl Sagan. But J.B.S. Haldane also said, the universe is not only stranger than we imagine, it's stranger than we can imagine. Somewhere out there, this may really be the case. We just haven't found the extraordinary evidence we need in order to support that claim. And there I'm done. Thank you very much. Yes, very happy to take questions. Please, do ask me questions. Go right ahead. Hang on, there's a microphone coming to you. Let's wait for that.
Probably my idea is not as crazy as aliens, but did anyone consider a three-body system where two stars are compact stars, and there is a rush lobe through which the matter is falling, the star is shrinking essentially, and the luminosity is slowly falling by few percent, and the third body is adding the periodic, making it a periodic, so that like you see.
Making it chaotic, hopefully,
yeah,
right?
Yeah.
I have not heard that one. You should write a paper, because that will make the 173rd explanation for Boyajian star, and it's as good as most of the other 172.
Maybe we can make some predictions so that
Go right ahead.
Good evening, sir. So, as the graph suggested that there is a dip of around 15 to 21% in the total the graph structure itself, and over the period of 4 years there has been a 3% dip in the luminosity of the star itself. So, and the prediction says that by 2021 there would be another event happening. So, how much would be an approximated value of the dip, considering the luminosity is also decreasing and an event of such kind is also in project? So will it be more than like 21% or less than 15%?
So the prediction of that model would be that although the star's overall light is still dipping, and if it continues it'll be a few percent lower by the time the object comes around again, the relative fraction of light should be roughly the same. Now of course they're saying that this is a swarm of asteroids, and a swarm of asteroids will evolve over time. So it won't be identical, but it should be roughly the same fractional dip in the star's light. So again, around about a 15 or 20% dip, if that's the right model. There's a hand there, come on. Hey, I'm talking about alien megastructures. You can't ask too crazy a question here. It's not possible.
We have on Earth also we have some intelligent life. So what are the prospects of our progress, human progress, so as to modify our genes through some technology of like CRISPR technology, which is upcoming, genetic technology, to modify our intelligence or enhance our intelligence so as to understand the universe much more deeper and much more in enhanced manner. So what do we think, that can we use CRISPR for every human being on Earth so as to enhance our knowledge of astronomy?
So just try saying that again. I'm not sure I've completely understood your question. Yeah,
genetic
okay.
technology which is CRISPR, CRISP.
Oh yeah, yep, right. So I don't know the answer to that question, but there are a few things that are being done which are quite interesting in that regard. So our ability to scan the radio spectrum is rapidly increasing, right? So telescopes like the GMRT, for example, are getting bigger bandwidths all the time, so they can look at more frequencies simultaneously. Telescopes like the Murchison Wide Field Array in Australia are able to look at a huge fraction of the sky at one time, so you can look at many thousands of stars and look at their signals. Ultimately, the Square Kilometre Array telescope will have enormous sensitivity over a wide band and able to look at huge areas of sky. So we'll be able to look for radio signals by many orders of magnitude more efficiently than we have been in the past, if we want to spend our time doing that. But of course, we're also beginning to detect other forms of signal. There's absolutely no reason why a sufficiently advanced civilization should be mucking around with old-fashioned radio waves. Radio waves may be as old-fashioned to them as smoke signals are to us. They could be using modulated neutrino bursts, they could be using gravitational waves, who knows what they could be doing. But at least these are new types of signals that we can begin to search for. We now have IceCube, which can detect neutrinos. We've got LIGO and other gravitational wave detectors which can detect gravitational waves. We can begin to search in other ways. So as our technology advances, our ability to detect other civilizations increases. The difficulty is that those civilizations are more than likely so much more advanced than us that their technology for signaling is as advanced over our technology is over people 1,000 years ago. And nothing of the way that we communicate our modern world would be detectable by people 1,000 years ago. And so it may be that advanced civilizations are simply invisible to technologies as relatively primitive as our own, which is why it's a very hard question to answer.
Am I audible? Yeah.
Ah, yes, now you're on.
After the Kepler telescope, the latest hot topic is TESS, Transiting
Yes.
Exoplanet Survey Satellite. So what do we expect with this new satellite? Will it throw some new light, especially on cases like these?
So TESS is going to be looking at relatively nearby stars. One of the difficulties with Kepler was it was looking at one patch of sky, and the stars that it was looking at were typically a very long way away, sort of distance that Boyajian stars, thousands of light years. And so that made it very hard to do detailed follow-up work. TESS is going to be looking at much brighter stars over the whole sky, which will enable us to do much more detailed follow-up on individual interesting cases. So if we find a star like Boyajian star detected by TESS, we'll have a much better chance of being able to really analyze it in a great deal of detail, because the star will be much closer, we'll be able to image it, we'll be able to do very high resolution spectroscopy on it. So it'll actually be a much nicer case if we find another Boyajian star. The question is, will we? And we don't know, of course. And by the way, does anyone know what's happened to TESS, right? It didn't go up today, right?
It was supposed to have launched yesterday.
Hmm.
It was stalled, and a new launch time has not been given yet. But one's
Okay.
hoping it'll happen this week.
Do we know why it was stalled?
Nope.
No,
No,
okay. It's a bit worrying. I hope it does fly, because
Yeah.
it's a wonderful mission.
It's a great mission.
So who was next? Another person in there, I see, and someone down the front. So down the front first, and then I'll do up the back.
So because we are talking about exoplanets, I just wanted to understand what are the signatures that we need to look for in exoplanets and that we can detect with near time frame technologies to see if they are habitable or not. What are the things that we can do
Right.
now with our tools available
Yeah.
to see habitability, and at a very broad sense, not like alien civilizations, but just
Well, in fact, we can do both, in fact. It turns out so that for planets that pass in front of stars, we can actually see the starlight passing through the planet's atmosphere, assuming it has an atmosphere, and then we can do chemical analysis of that atmosphere. And so we already know that there are, surprise, surprise, water and nitrogen and carbon dioxide in the atmospheres of some of the planets that we've already detected. Now, none of that is a surprise. But if we were able to look at a star and we began to see ozone or other out of equilibrium chemical constituents that shouldn't be in that sort of an atmosphere, then we might be saying that we're detecting some form of alien life on that planet. So it is possible. Now that's something beginning to be done now. It's been done in a few very simple cases for not very interesting and certainly not habitable planets so far. But with the next generation of giant telescopes, with the 25, 30 and 39 meter telescopes that are being built for the next decade, we will be able to do that for habitable zone planets of the sort that TESS might be discovering, hopefully, very soon. So yes, there's real prospects with genuine near-term technology for doing precisely that sort of thing, determining whether a planet is habitable. You know, if it's habitable in our terms, it's got a certain mixture of oxygen, etc. in the atmosphere, we will be able to detect that. And we will be able to detect certain forms of disequilibrium that a civilization might cause on a planet. So definitely possible. Up there. Oh.
Hello. Hello. Yeah. First of all, the talk was very amazing. I learned a lot of things. But I just want to say one thing, that maybe, as you say, that the luminosity is decreasing. So maybe it's dying with some different disease, like kind of, let's say, like a different star dying with something different way.
Maybe, but we don't have a good theory for how you'd kill a main sequence star. This star should last for another billion or more years on the main sequence. And so we don't know of any stars of that type, and there are many of them in the galaxy. It's not a rare type of star, which are suffering from this disease. Yeah. You could be right. I'm not saying you're not, but we just don't know. We don't have any good theory for how that could occur. We just don't have a good theory for it.
Good evening, sir. Actually, I read a joke yesterday that a teacher asked his student that if you were a Superman one day, what would you do? So the student says that I'll go to the outer space and find aliens. So the joke here is Superman himself is an alien.
Indeed.
So if some other civilizations are observing us, my question is, what kind of signal shall we send that that civilization is sure that this is not some kind of natural phenomena, these are aliens out there?
So we've only had significant radio technology on Earth for the last 100 or so years. So stars within about 100 light year radius could be detecting us now by our radio signals. It wouldn't be hard to do. And in fact, the power of our radio signals, the sort of very strong radar signals that are being used, can in fact be seen to very large distances across the galaxy. The difficulty is, of course, they'll take thousands and thousands of years to get across the galaxy, but in principle they'll still be detectable when they're halfway across the galaxy. So we're already emitting signals that would mark us unambiguously as a semi-intelligent life form. But you could have done more than that. You could have used the technique I was just talking about earlier and look through our atmosphere and tell, ever since the Industrial Revolution, that we're a species that knows no better than polluting our own planet, right? We've been putting smog and carbon dioxide and ozone and other things into our atmosphere, and all of that would have been detectable by the techniques I was talking about earlier for the last 200 or 300 years, right? Before that, you might have been able to tell that we're a habitable planet by looking at our atmosphere, but there wouldn't have been any signals of intelligent life.
Yeah, there are many, many fans of I Love Lucy out there right now.
Yeah.
Yes, back to this gentleman here.
So the present generation of computers have done quite a bit understanding of universe. So the next generation of computers, which are the quantum computers upcoming, through which will help again us to enhance the understanding of the universe. So how these quantum computers plus more advanced instruments in telescopes will help us to enhance our knowledge of universe?
So if the question is, what are new telescopes going to be able to tell us about the universe? The answer is an enormous amount, okay? The next generation of telescopes, let's talk about first optical telescopes, right? The giant telescopes are going to be able to see every black hole at the center of every galaxy throughout the entire visible universe. They're going to be able to directly image planets around many stars in our galaxy. They're going to be able to detect whether there is life or habitability on a handful of relatively nearby planets. In the radio, we're going to be able to use the square kilometer array to map out the structures of the universe very shortly after the Big Bang. With LIGO, we're going to be able to see the dance of neutron stars and black holes around each other and what happens when they merge. So with these telescopes, we've got a whole new range of windows on our universe that are going to give us extraordinary power to see the universe. We've gone from not knowing anything about the universe, from having to look at the stars with our naked eye, to being able to see the electromagnetic radiation and even the neutrinos and the gravitational waves from much of the observable universe over a period of a few hundred years. So we've gone from being blind to fully sighted as a species, as a civilization living in the universe, over a remarkably short period of time. Over my career, over Shomac's and my career, we've gone from not knowing the size and age of the universe to within a factor of 2,
Yes.
to knowing it to better than 1%, right? The fact that, my next big project is to measure the age and size of the universe to a precision of better than 1% is extraordinary. If you told me that when we were in grad school together, I would have laughed at you because we couldn't measure it to a factor of 2. And all of that is driven by technology. Astronomy is a completely technology-driven subject because we are forced to observe the universe. We cannot do experiments in the lab. I cannot build a star in the lab and look at it. I've got to observe the universe. So I'm completely at the mercy of what technology is available. But the advances in technology have been so stupendous over our combined career that our knowledge of the universe has gone from basically what Copernicus knew to an extraordinarily more precise and detailed and varied knowledge of the universe.
Thanks. We are winding down here. Just as you know, we are webcasting this live, and we have people watching this all over the world, and we're getting questions from them as well. So I'm going to ask you a question that's come
Sure.
through from the webcast, and it's Harshada Gurav who's asked, this star is so far away that there must be multiple objects on the way. How are we sure that the luminosity is dropping because there are eclipsing objects along the line of sight?
Right. So in fact, it is possible. The difficulty there is moving things across the line of sight fast enough. Remember I said that these eclipses are happening on periods of half a day or so. Things in the interstellar medium move very, very slowly relative to each other in general. And so the likelihood of something zipping across the star is relatively small. So that's one reason. Another reason is that we've looked at 100,000 stars, and only this one star is doing that, right? And it's hard to believe that the interstellar medium, which should be in front of all the stars along the Kepler line of sight, is so concentrated and interesting for this one star, but for a whole bunch of stars, only a tiny fraction of an arc second away, nothing's happening at all. And that's very hard to believe as well. So those are the reasons.
First of all, I just wanted to thank you for the talk. It was really awesome, by the way. And my question to you is, I just recently read an article about how astronomers are planning to take a picture of a black hole using a radio telescope, I guess. So how exactly would that work, considering the fact that a black hole has a reputation for just sucking in all the light it has?
Yes, so you're not really taking a picture of the black hole itself. So black holes which are on an astronomical scale, no black hole is perfectly black. Stephen Hawking, who just died, showed that in fact they're all emitting a tiny amount of radiation. But for black holes that are as big as stars, or indeed millions of stars, which are the ones we see in astronomy, the amount of that radiation is so tiny that we really cannot detect it. So black holes, to all intents and purposes on astronomical scale, really are black. They're not seeing that. What they're seeing is structures around the black hole, matter falling into the black hole, an accretion disk of matter around it, and the jets coming out of it. Those things we can see. We can't really see the black hole itself. But we can see a lot of things around it, and that tells us a lot about the environment of the black hole. It tells us things like the mass of the black hole and various other things as well.
Okay, does anybody have a question that's related to today's talk? Not just anywhere in astronomy. Here, do you? No? No? You pass?
There's one over there, behind you.
Here.
Good evening, sir. The talk was wonderful, by the way. I would like to draw your attention towards the errors that are produced in instrumentation. I mean, it wasn't the case for the Tabby star, but if there happens to be a case where there is an extraordinary event happening, and we don't really know that whether the event is actually happening or it is the results are being produced due to an instrumentation error or a signal processing error. So what are our ways by which we can make sure that this isn't the error which is being produced by an instrument, and this is definitely an astronomical event that is taking place. So how do we make sure that?
So look, this is an issue that all astronomers deal with all the time, right? I mean, this is half of what astronomy is doing, actually, is checking reproducibility. And so the answer is, of course, that you try and do things multiple ways with multiple different instruments. You get different groups working independently of each other with different types of instruments, with different types of errors in them, all looking at the same thing. And if they agree, then you've got reproducible data and you're happy. But of course, this doesn't happen sometimes, and when that doesn't happen, we reject it. It's not science. And so this is something that we do all the time. In fact, we're increasing our levels of rigor in this area. So a lot of work is being done now where it's blinded. In fact, where you do the analysis and you don't know whether you're working on a simulated data set or the real data set, in order to check whether your analysis, you're not working towards an answer because you've got a bias when you set out. So we're doing more and more to be more reproducible, to blind and even double blind ourselves as to what we're actually doing. So it's a big issue for us, but we're very aware of it and working hard on it all the time.
It's getting late, and I think we are winding down now. So I'm very, very happy that there were so many questions today. I'm sure Matthew is too. Let's give Matthew another big hand and draw the huge applause. And thank you very much for coming.
Thank you all very much. You're a great audience.